So my interests are in biotechnological solutions as a possibility for reducing our reliance on inorganic fertilizers. We've heard a lot today about the detrimental impacts fertilizers have, the primary source for pollution from agriculture, driving eutrophication and biodiversity loss. We've heard a lot about nitrogen in that context, but phosphate is also a major driver for eutrophication. And then, of course, the major cause of greenhouse gas emissions from agriculture. And if we look at, we've already heard today that we've almost doubled, more than doubled the global nitrogen cycle with anthropogenic use of nitrogen. But as we go forwards in an expanding population, we're looking to double that again in a business as usual scenario. So far from anticipating less nitrogen use in a business as usual scenario, we're actually considerably increasing nitrogen use to support the increasingly demanding population. So here I'm borrowing a couple of figures from one of Nathan's papers. In the developed world, all of that fertilizer use is a big driver for pollution and unsustainability of the system. But the side that we haven't really discussed very much today is the opposite side, which is in developing nations, is the lack of access to these nutrient fertilizers that drives poor production in their food systems. And in places like sub-Saharan Africa, they're really only achieving 15 to 20% of the potential yields. From my perspective, I would say that's the greatest opportunity for increasing food production, because they're really underperforming high quality arable lands that are massively underperforming at the moment, and there's huge potential to increase productivity in those regions. But if we don't do anything, we will see a business as usual scenario. We'll simply see a massive increase in fertilizer use in sub-Saharan Africa as the countries develop and the farmers can start to afford to use those fertilizers. So I'm interested in what scenarios there are to bypass that dependence on inorganic fertilizers. And I work on these beneficial associations that happen between plant roots and microorganisms present in the soil. And in particular, we focus on two associations, the arbuscular mycorrhizal association, which is an association between plant roots and fungi. And the fungi heavily colonize the roots, and they'll also ramify out into the soil, and they may produce a much larger surface area for the uptake of nutrients. They're particularly well known for their acquisition of phosphorus, but they've also been demonstrated to be helping in the uptake of nitrates, and they also benefit in the acquisition of water, and it's possible they're also helping in the acquisition of potassium as well. So they're actually quite a broad service to the plant in the acquisition of nutrients from the soil. And the second association that we work on is that between legumes and nitrogen-fixing bacteria, where these nitrogen-fixing bacteria can access the atmospheric nitrogen, providing the plant with a completely novel form of nitrogen coming from molecular dinitrogen in the atmosphere. And to a legume, nitrogen fixation can deliver all of the legume's needs for nitrogen. So it really can absolutely replace the totality of the nitrogen that we provide through agricultural fertilizers. So cereal crops have the ability to form arbuscular mycorrhizal associations, but they lack the nitrogen-fixing symbiosis. But the fact that they form the arbuscular mycorrhizal associations doesn't mean it's very extensively used in agriculture, because actually what happens is the plant recognizes that they've added lots of fertilizer. The plant sees that there's lots of nitrogen and phosphorus around, and it chooses to not to engage with these beneficial symbionts when there's ample nitrogen and phosphorus. So although our cereal crops have this capability to associate with mycorrhizal fungi, most times in most intensive arable farming systems, they're really mycorrhizal fungi are really not very extensively utilized. And the reason for that is simply the fact that when the plant goes to the fungus for acquisition of nutrients, it pays a price for those nutrients. So it has to exchange carbon from photosynthesis for these nutrient services from the fungus. And in fact, every single molecule of carbon in the fungus is derived from the plant. The fungus is a carbon auxotroph. It can't get carbon from any other source but from the plant. And in that regard, it's actually a really good way to sequester carbon, because you're moving carbon from photosynthesis through the plant down into the soil and building these complex fungal hyphal networks entirely from carbon derived from photosynthesis. But as I said, when the plant recognizes that there's ample nutrients around, as in the case when we fertilize, it just takes those nutrients up for free. It's not willing to pay the price that comes with symbiotic associations for the uptake of these nutrients. So although most of our cereal crops can form this arbuscular mycorrhizal association, this is the reality that we have in most of our cropping systems in the developed world. And that's rather unfortunate, because in an agricultural context, you actually want the mycorrhizae there when you fertilize. You've got a much, much more efficient network for capture of those nutrients when you fertilize if you have an arbuscular mycorrhizal network sitting in your soils. You'd get much less loss out into the environment for driving eutrophication, and theoretically you could get more productivity with less fertilization. So step one for me in reducing agricultural reliance on inorganic fertilizers is just better use and better capture of what is already applied. And for that, I would like to see something like this, where we develop complex mycorrhizal networks in our agricultural soils, even or especially at the time when we fertilize. So we have a much more efficient mechanism for the capture of those nutrients, and theoretically would lose less nutrients out into the environment. Well, we've achieved this in the lab, so we know we've discovered the transcription factors that control this drive to the symbiotic state. These transcription factors are tightly regulated by the nutrient status, so they're normally in a normal cereal plant, they're only activated when the plant is starved for nitrogen or phosphorus, and they're completely suppressed when there's ample nitrogen and phosphorus around. So that wiring means that you only activate the symbiotic state when you're starved for nutrients. Now, if we misregulate these transcription factors, I'm going the wrong way. If we misregulate these transcription factors, I'm totally going the wrong way. I'm sorry. I was trying to hit the laser button, and there you go. Okay, if we misregulate these transcription factors, so here we've got a wild-type plant on the left, and a bunch of lines that are overexpressing these transcription factors. There's no effect when we look under low phosphate conditions where you're promoting mycorrhization. So here we're measuring the percentage of the root that's colonized by the fungus, and you can see it does get massive colonization by the fungus. Up to 75% of the root will be colonized by arbuscular mycorrhizal fungi. And you can see when we go to high phosphate conditions, this is a low phosphate wild type, this is a high phosphate wild type. You can see this massive suppression of the mycorrhizal colonization driven by those high phosphate conditions. But when we overexpress these transcription factors, you can see that under high phosphate conditions, some of these lines are getting colonized almost to the same level as the wild type under low phosphate conditions. So we've demonstrated, at least in the laboratory, that we can override this nutrient suppression of mycorrhization. We're just setting up now to move these are barley lines, engineered barley lines, out into the field to look at their effectiveness in the field, and in particular their effectiveness at limiting the loss of nutrients from the agricultural environment. So that's step one, is really just to optimize the levels of the utilization of the nutrients that are currently applied. And step two for me is introducing this the nitrogen-fixing symbiosis and moving it from legumes into our cereal crops so that we can basically remove nitrogen entirely from the system and allow our cereal crops to be utilize this atmospheric form of nitrogen. Now, this has been a very aspirational area for plant biotechnology for many years, and it would seem like it's a really challenging thing to move something as complex as nitrogen fixation into cereals. But we really have a benefit here because evolutionary, so the arbuscular mycorrhizal symbiosis emerged 450 million years. This is a phylogeny of the whole plant kingdom. It emerged extremely early in the evolution of land plants and probably facilitated the colonization of land by plants. And as a result, the mycorrhizal symbiosis is pretty well ubiquitous across the plant kingdom. Now, in contrast, when the nitrogen-fixing symbiosis evolved, which was about 100 million years ago, it's restricted to a group of the angiosperms. Well, what we've found from many, many years of genetic studies of this process of nitrogen fixation is that most of the genetic components that are required for nitrogen fixation, they didn't evolve at this point. They evolved down here at the base of the land plant. And that's because the arbuscular mycorrhizal symbiosis is really the mother of the symbiotic processes. And we just demonstrated that, in fact, many of the genetic components that evolved down here at the base of the plant kingdom underpin all intracellular symbioses in land plants, independent of the symbiont that's utilized. So in other words, most of the genetic components that are needed here to support nitrogen fixation actually evolved down here and are already present in our monocotyledonous crop plants. And just to demonstrate this further, when there are a number of species of plants that have lost the arbuscular mycorrhizal symbiosis, and when they lose the arbuscular mycorrhizal symbiosis, they rapidly lose many, many genes that are required for that. And they lose upwards of 120 genes associated with the loss of the arbuscular mycorrhizal symbiosis. In contrast, species that have lost nitrogen fixation but have maintained mycorrhization only lose 3 genes. So, and that's in part because underpinning all of these genes are underpinning that nitrogen fixation symbiosis. So we know that there's in excess of 120 genes that are necessary for this intracellular symbioses. But differentiating between a nitrogen fixing plant versus a mycorrhizal plant seems to be only 3 genes that differentiate those species, at least from an evolutionary perspective. Now, that might be wildly ambitious, and we're obviously currently testing, in the middle of testing, whether we require, if those 3 genes alone are sufficient to convert an arbuscular mycorrhizal plant into a nitrogen fixing plant. But the key take-home message here is that actually cereals already have a lot of the components that are necessary to support nitrogen fixation, and we're building upon that mycorrhizal state in order to drive the engineering of nitrogen fixation in cereals. Thank you.